Okay, sorry about that, guys. Had to take a quick break here and make sure I knew what I was doing. So what I ended up doing here was change gears just a little bit. There are other ways to do this, but since I started it this way, I wanted to finish it off. So since I had an H plus value, what I went down here and did was I said that, look, if I know the concentration of H plus, I know the product of H plus times OH minus is 1 times 10 to the negative 14th. So then I found the concentration of OH minus in this salt solution as 5 times 10 to the negative 4th. At that point, I said, look, I already know that this is the hydrolysis equation for the Z minus ion. And I know that the X value that would be formed plus X was 5 times 10 to the negative 4th. So because it was coming from a 0.15 molar solution of NaZ, that meant that I had 0.15 molar Z minus to begin with, and I'm going to subtract the 5 times 10 to the negative 4th. So coming from my icebox and scooching down here to my Kb expression, I ended up with 5 times 10 to the negative 4th squared over this, equaling out to this. Then I use Ka times Kb for acids and conjugate bases, and bases and conjugate acids equal to 1 times 10 to the negative 14th. So that was a much longer roundabout way than could have been done, but it got me to the right answer, and that was really the part that I wanted to make sure that I got across to you guys. All right, so let's see what's going on here with number 27. Calculate the pH of 0.1 molar aqueous solution NH3, and it's saying that Kb of NH3 is 1.77. So let's think about it. If it's giving me a Kb value, and I guess I can write that up here, we're going to think that the NH3 is acting like a base, and if it acts like a base, it's going to accept a hydrogen, so we're going to form some NH4 plus and some OH minus. And at that point, this one's not so bad. This is just going to be a traditional icebox type problem. I'll get this paper out of the way here so it's a little less distracting. And we're off to the races, so we go 0.1 minus x, so 0.1 minus x here. We're ignoring the water, and we're going to go 0 and 0. We're going to go plus x, x, x. And we write our K expression, Kb is equal to, and we know that it's 1.77 times 10 to the negative 5th. It's equal to x squared over 0.1 minus x. So x squared over 0.1 minus x. Use an approximation here. This is different enough from 0.1, a factor of 10 to the 4th. Is that right? 10 to the 4th? 1 times 10 to the, yes, 10 to the 4th. And so you end up with the expression simplifying down. 1.77 times 10 to the negative 5th times 0.1 just equals x squared, because subtracting x from the 0.1 is going to yield basically no difference. And so we're going to take the square root of that product, 0.1 times 1.77, negative 5. And if I can type that into the calculator correctly, there we go. And we'll square root that number. And I'm getting a 0.00133, and we remember what that is. X is 0.00133, and that is the concentration of OH minus. It asked me for pH, so you just have to make sure that you remember what you're doing there. If I want to take it in this direction, I'll go POH is the negative log of the concentration of OH minus, 0.00133. Negative log, and then I'm going to do 14 minus that answer, and I get about 11.12, which is the answer there. So using our old friend pH plus POH equals 14. All right, and last but not least, that's on the page. Definitely some longer, more difficult problems as we move into this portion of the test. But again, really just critical stuff for you guys not only to know how to do, but how to do well and right all of the time. Calculate the pH of, camera, sorry about that. Calculate the pH of a 0.0787 molar aqueous sodium cyanide solution. So off we go, sodium cyanide. NaCN minus. The Na will be irrelevant, so we're most concerned with the cyanide ion and its hydrolysis. Cyanide ion will act like a reasonably strong conjugate base coming from the weak acid, HCN. And so we HCN plus OH minus. And we're going to try and write a Kb expression. Excuse me. We're going to calculate the pH. And if we know what the Kb is, that's reasonably helpful. So we're coming from a 0.0787 molar solution. And we're going to ice this. And we're going to say that we've got nothing, and we add this, and we add this. And so we go with 0.0787 minus x, and x. And my camera is doing all kinds of silly things. I am very sorry about that. So we're going to then say Kb is equal to 4.9 times 10 to the negative 10th equals x squared over 0.0787 minus x. Very different, so we can use an approximation here. So I'm going to end up with 0.0787 times 4.9 times 10 to the negative 10th. And we're just going to set that equal to x squared. Let's see what x works out to be when we do that math. And I need a new camera if I'm going to do this for you guys. Negative 10th square root. And I'm getting something like 6.21 times 10 to the negative 6. 6.21 times 10 to the negative 6. Then you go back and remember what that is. That is the that is the OH minus concentration. So I'm going to go ahead and get a POH and then just do a quick conversion to that. Negative log. I'm getting a POH of about 5.207. So pH plus POH equals 14. And so at the end of all of this, we're getting a delightful pH here of about 8.79. And that answer is E. Whew. Big deep breath after some of these. The good news is once you're good at them, they're pretty easy. But it's the getting there that's sometimes the trickiest part. All right, let the camera settle down. Maybe I'm going to put this a little further down into the light. All right, here we go. Determine the pOH of a KF solution, giving us a Ka value. So what do we concern ourselves with? We've got K, that's not even a K. We've got KF. Not going to worry about the K. I am going to worry about the F because the F minus in water could certainly act as a base and make some HF and some OH minus. So what are we going to do here? Gosh, you know what? This is an awful lot like the other problem here. So if I know the Ka, no, maybe not. If I know the Ka, all right, I can take Ka times Kb equals 1 times 10 to the negative 14th. If Ka is 7 times 10 to the negative 14th, we can get the Kb for the conjugate base, and F minus is the conjugate base of HF, 1 times 10 to the negative 14th. So I'm getting a Kb value. And now as I think back, this would have been a much easier way to do that other problem that I stopped on. Oh, well, we continue. So I think I did that math wrong. 1 times 10 to the negative 14th over 7 times 10 to the negative 4th. That's a big difference there. So let me change that up. And more like 1.43 times 10 to the negative 11th. All right, whew, now we're off to the races. Let's finish this thing up. So I'm going to end up with a 0.35, a minus x, an x, and an x. So my Kb expression 1.43 times 10 to the negative 11th will equal to x squared over 0.35 minus x. An approximation is certainly valid in this case. So we're going to take the 0.35 and multiply that by the 1.43 times 10 to the negative 11th. And then don't forget to take the square root of that. 2.23 times 10 to the negative 6. 2.23 times 10 to the negative 6. That is the concentration of OH minus. So to get POH, negative log of concentration of OH minus. And I am keeping my fingers crossed that I have done all of this correctly and not led you astray. 5.65b. Hoorah. All right, final stretch here. Number 30. We've got an answer of D. We're trying to find the Ka for formic acid. Oh, get straight there, papers. Boom. Ka, formic acid. And we want to find the pH of sodium formate. Sodium will be irrelevant. Lots of relatively strong conjugate bases here. So we're going to look at the HCO2 minus in water, and it's going to peel off an H plus, form some H2CO2 plus OH minus. If I know the Ka, I can certainly find the Kb, the same process as last time. Ka, Kb, 1 times 10 to the negative 14th. Oh boy, oh boy, oh boy. 1.8 times 10 to the negative 4th. Kb, 1 times 10 to the negative 14th. Kb, 1 10 to the negative 14th divided by 1.8. Sometimes a little silence there is good. So I've got a Kb expression, and now I think we all know how to write this stuff. Hopefully, if it's starting out at a 0.1 molar solution, we're going to end up with Kb that looks like this. 5.55 times 10 to the negative 11th equals x squared over 0.1 minus x. Certainly, we're going to approximate that one. So 0.1 times that square root. And I've got 2.36 times 10 to the negative 6, 2.36 times 10 to the negative 6, and just be very careful. That x value there is the concentration of OH minus. So when I do negative log of this number, I'm ending up with a POH, the negative log of my 2.36 times 10 to the negative 6. And draw a little line here for clarity. Negative log of answer. And so my POH is 5.628. Subtract that from 14, and I should be at my pH value, 8.37. The answer is D. All right. 31. 2 more to go. Hang in there, all right? You guys are doing great if you are sticking it out here and doing the extra work so that you know how to do these. It will pay magnificent dividends for you. Here's the wonderful thing. You look at this and you're like, oh no, Ka1, Ka2. We got to remember that where does most of the hydrogen come from? It comes from that first dissociation. So we're really and truly going to be focused on the Ka1. So we think about our sulfurous acid, H2SO3, is going to be breaking apart into HSO3 minus and H3O plus to the tune of 1.7 times 10 to the negative 2. 1.7 times 10 to the negative 2. We know from our icebox these end up looking like x squareds minus the, x squared over the original concentration minus x. Now this one's a good one. Would we expect an approximation to be a good or a bad idea? You focus your attention here, 10 to the negative 2. This would be 1.63 times 10 to the negative 1. These are not very different, so subtracting x would matter. So choose your favorite method to figure out x, because if we find x, then we've got the concentration of H+. I myself, I'm going to try a graphing technique. And so I'm basically rewriting this guy as 1.7 times 10 to the negative second times 0.163 minus x equals x squared. Do a little algebraic manipulation. I'm going to say x squared, and I'm going to subtract. So I'm going to add that over, so that becomes plus 1.7 times 10 to the negative second x. And then this positive times positive gets subtracted over, so then I've got minus 1.7 times 10 to the negative second times 0.163. And I went a little off the screen there, sorry about that. And let's plug that in, x squared plus 1.7 e negative 2x minus 1.7 negative 2.163. And if I've got that all correct, I'm going to use my trace calc feature on the calculator to calculate a 0. I know that I've got to be somewhere between 0 and my 0.163. I'm getting a 0 of 0.0448. So x is 0.0448. So then I should be able to go a negative log of 0.0448. And let's just hope that that gets me to an answer about 1.34. Now that is not the answer that I see. So what did I do wrong here? Let me go back and double check something. X squared 1, okay. Now it could be due to a rounding error. What did I get? I got 1.34. Because it's very late, I'm going to chalk that up to a rounding error. It's also conceivable that that tiny bit of extra came from the KA2. I might have to look at that one a little bit more, and if I find something out, I'll share it in class. All right, last but not least, let's go with 32. The answer was 0.045. If it's 2% dissociated, a couple of you guys just forgot what 2% dissociation means. What that really means is when we look at this, all right, I'm trying to find the original concentration. So the original concentration was X, all right? So we know that out of my X, I had 0.02x that was, for all intents and purposes, my hydronium ion. So I've got an acetic acid, so we know that that's going to be HC2H3O2. Going to dissociate into H plus and C2H3O2 minus. And the only thing that I've got is a Ka value. So we can go ahead and say Ka is 1.8 times 10 to the negative fifth. We have to think about these guys, right? So I know that I've got a 2% solution, which means that from my original concentration of X, I only had 0.02 of X. That was hydronium. And that's really where the key is here. We know then that at equilibrium, this is going to be 0.02x, and this is 0.02x, and this is going to be x minus 0.02x, which last time I checked is 0.98x. So I'm going to try and do some fancy math here, and I'm hoping that I've got this right, because it's real late, and I just kind of want to go to bed. So at this point, I've got this expression. I'm going to go 1.8 times 10 to the negative fifth, 0.02 squared. Make sure that you're not doing anything silly. That's 4 times 10 to the negative fourth, x squared, over 0.98x. We're going to get rid of an x. And so hopefully my algebra is all making sense here. 1.8 times 10 to the negative fifth. I'm going to multiply the 0.98 over. And then I'm going to divide by 4 times 10 to the negative fourth. And I am hopeful that 0.044 is the answer I got. And it depends really on how you round it, I think, perhaps. And at this late hour, that is close enough for government work. So hopefully those of you that hung in there, this was helpful to you. And again, if you need any help, we're going to do a review session Sunday evening. That's March 14th, 7 to 8:30 in my classroom. And we'll do a retest in my classroom on Friday. That would be March 18th at lunchtime. for those of you who would like to improve your scores on this test. Okay, thanks so much, and happy chemistry. Bye-bye.